This is a video abstract for the paper, An Operator-Algebraic Formulation of Self-Testing, by Connor Paddock,
William Slofstra,
Yangchen Zhao,
and Yangchen Zhou.
In a Bell scenario, two spatially separated parties, Alice and Bob, each receive inputs from finite sets X and Y respectively, and return outputs from finite sets A and B. Alice and Bob's behavior in the scenario is described by the probability PABXY, that they output AB on input XY. The collection of all these probabilities is called a correlation.
A correlation can be realized in quantum mechanics if it has a quantum model, a pair of finite-dimensional Hilbert spaces HA and HB, POVM measurements MXA and NYB on HA and HB respectively, and a joint state psi in HA tensor HB such that the probability of measuring A and B on inputs X and Y with these measurement operators and state agrees with P. Given a model S, we can always add an auxiliary system that doesn't interact with the measurements to get another model with the same correlation. So every quantum correlation has many different quantum models.
A correlation is a self-test if all quantum models for the correlation are equivalent, up to local isometry, to some fixed model, called the ideal model, plus an auxiliary system. Or more formally, if there is a model S tilde for P, such that for any other model S, there are Hilbert spaces HA-OX and HB-OX, local isometries IA and IB, and an auxiliary state OX, such that applying the local isometries to S yields the ideal model S tilde plus the auxiliary state. This formal definition of self-testing has been very successful, and self-testing has become an important concept in quantum information, used in both theory and experiment for things like entanglement certification. However, the definition is somewhat ad hoc. The auxiliary system needs to be incorporated somehow, but why exactly this definition with local isometries? In fact, many variations of this definition have been used since the concept of self-testing was introduced 20 years ago by Myers and Yao.
In this paper, we look at a more mathematically motivated definition of self-testing. We say that P is an abstract state self-test if for any sequence of inputs and outputs, the bracket of psi with the corresponding product of measurement operators does not depend on the choice of model for P.
The name abstract state self-test comes from operator algebras. Quantum models can also be thought of as abstract states on a tensor product of C-star algebras, in the sense that every quantum model gives rise to a finite-dimensional abstract state, and every finite-dimensional abstract state can be turned back into a model. A correlation is an abstract state self-test if it arises from exactly one such abstract state. No up-to-local isometries required.
Our first main result is that if P is an extreme point of the set of finite-dimensional quantum correlations CQ, then P is a self-test for quantum models, if and only if P is an abstract state self-test. Abstract state self-tests are the same as ordinary self-tests. The same equivalence holds if we look at self-testing for other classes of models, like quantum models with projective measurements rather than POVM measurements, as long as an extra technical condition is met.
In the self-testing literature, it's been more common to look at self-testing for projective models than for POVM models. However, our second main result is that for two large classes of correlations, binary correlations and synchronous correlations, being a self-test for projective models is the same as being a self-test for POVM models. This covers prominent examples of self-tests like the CHSH gain and the tilted CHSH gain, the Mermin-Paris magic square, and so on.
We do not know if it's possible for a correlation to be a self-test for projective measurements, but not a self-test for POVM measurements. A number of subtle mathematical questions like this have come up in our work and recent work by other authors, and we think that resolving these questions will be an important part of developing a deeper understanding of self-testing.
Some of the most interesting questions for us arise from commuting operator models, which are more general than tensor product quantum models. The standard definition of self-testing does not have a clear generalization to commuting operator models, but abstract state self-testing generalizes naturally. Using this definition, we show that a correlation is a self-test for finite-dimensional commuting operator models if and only if it is a self-test for quantum models in the standard sense. Having a notion of self-testing for commuting operator models raises the possibility of interesting connections with operator algebras, which we leave for future work.
Another thing we don't address in this paper is robust self-testing. What happens for models that achieve a correlation close to p? While robustness is crucial for applications of self-testing, ignoring it at this stage allows us to concentrate on the non-robust theory. Robustness is something we hope to incorporate into abstract state self-testing in the future.
For full details and references for everything, please see the paper.